Exercise 9. Write a system of inequalities whose solution set is the shaded region. Okay, as we look at this shaded region, it's a quadrilateral here, trapezoid actually, but what's interesting also is that it is convex. Okay, so we might here first observe the region is a convex polygon, and this means we know a system of linear inequalities will work. Okay, so we can imagine this as being the intersection of four half planes. One will be to the right of this line segment, another one below this line segment, another one to the left of this, and another one above that. Okay, to organize our solution here, maybe we come in and start giving these lines a name. Okay, this is a line segment, but it's part of a bigger line which we could consider to be a L1. This could be L2, that line segment there. This can be L sub 3, and this line segment can be part of L sub 4. Alright, now let's start here. L1. What about an inequality whose boundary line is here and below? What to do? Let's get the boundary line. Let's see. What do we know about this line? These 2 points lie on this line. Okay, so maybe you consider point slope form. That's the y minus y1 equals m times x minus x1. Okay, well, to get this form resolved in this specific case, we'll need the slope first of all. Okay, m slope equals change in y over change in x, or y sub 2 minus y sub 1 over x sub 2 minus x sub 1. In this case, I always call my right-hand point the sub 2. So let's see, we have 5 minus 4 over 6 minus 3. That will be 1/3. Okay, now we have 2 points to choose from in filling in the rest of our point slope form. I suppose 3, 4 has the easier coordinates, so let's go with that. We got y minus 4 equaling m 1/3 x minus 3. Okay, and sometimes you want to make this look a little nicer, so let's multiply the 1/3 on through there. That's 1/3 x minus 1. Add 4 to both sides. Y equals 2 1/3 x plus 3. Give ourselves a little graphic check. Now this is in slope-intercept form. We can sort of extend here and agree that this seems to have a slope of 1/3 and a y-intercept of about 3, so it's looking pretty good. Now this is the boundary line. What about the inequality? As for this kind of line, we can think in terms of above or below, since we have this y equals to mx plus b form here, and we clearly want to be below this line, and this is dashed, so we don't want to include the equality cases. We simply want y less than 1/3 x plus 3. Okay, there's L1. L2. Alright, what about this? So we have this vertical form coming to mind. That's the x equal to constant. In this case, the x is specifically held to be equal to 6. Now, which side of the line do we want? We want to be to the left of that. So we want to be having the x less than 6. Also, this is solid, so we need to include the equality case as well. We've got x less than or equal to 6. Okay, let's go on to L3. In this case, it's a horizontal line. So the horizontal form comes to mind. That's y equals a constant. In this case, the y is held to be 2. Now that is the boundary line. The inequality we needs to include this boundary line and everything above it. Thus, we're thinking y greater than or equal to 2. Okay, L4. Now this is again a vertical line. So we're thinking x equals to a constant is the basic framework of the equation. As looking at the points here, the x is held to be equal to 3. Now in this case, we need the half plane that lies to the right of this line. So we'll have to use a greater than sign for the inequality, and it's a solid line, so include the equality case as well. This leaves us with x greater than or equal to 3. Okay, so let's summarize here. The system could be this. Okay, this one, y less than 1/3 x plus 3. L2, x less than or equal to 6. L3, y greater than or equal to 2. And L4, x greater than or equal to 3. Alright, let's give this maybe just one check before we walk away. Let's see, what could we do for a check? We could select a point that's surely in our solution set here that we see. So let's go over here. X is 4, okay, and y could be 3. That's certainly in the solution set. So 4, 3 is clearly in the region. So let's try substituting. Into the inequalities. Alright, the first one, y 3, how about that being less than 1/3 times 4 plus 3? Okay, well, here's 3. This is 3 3/4 on this side, greater than 3. True. Okay, second inequality. X less than or equal to 6. X is 4 in this case. 4 less than or equal to 6. True. Okay, third inequality. Y greater than or equal to 2, meaning that substitutes in with a 3 for the y. Greater than or equal to 2. True. And lastly, x greater than or equal to 3. The x is 4. 4 greater than or equal to 3. True. Okay, this all looks pretty good. Let me just kind of organize this a little bit here. This check is down here. The main solution is over here. Alright, looks good. Exercise 11. Write a system of inequalities whose solution set is the shaded region. Okay, let's see, what do we notice about this shaded region? Well, two things that are important. One, it's convex. Two, it has straight line boundaries. Okay, so observe the region is convex and has straight line boundaries. Okay, so what does this tell us? We can use a system of linear inequalities. Okay, well, let's see. To get started on this, we might go in here and label our lines. Here it could be line 1, L1. This could be L2. This could be L sub 3. This here could be L sub 4. Okay. Now, let's see. For L1, what have we got here? In L1's case, you notice we have the x-intercept and the y-intercept clear. We could choose to work off of intercept form. Intercept form, that's x over a plus y over b is equal to 1. In this particular case, it is an x over 6 plus y over 8 equaling 1. Now, as far as making an inequality goes, well, first of all, it's a solid line, so we need to keep the equal sign as part of it. And let's see here. Let's say 0, 0 needs to be a solution to this inequality because we are talking about the half plane down in this direction like so. So let's put 0, 0 into this and get an inequality that makes it true. If 0, 0 goes in here, we have 0 here and 1 here. Well, that means less than would make it true. So this finally then gives us x over 6 plus y over 8 less than or equal to 1. That can be our first half plane there. Okay, L2. Well, let's see. Looks like horizontal form will be the basis of our line here. Horizontal form, that's the y equal to constant case. In this straight line across here, that's going to be a y equal to 0. Okay, now that's the boundary line. As far as the inequality goes, we want to be above it. So we need to have the y greater than. It's a solid line, so greater than or equal to. Okay, let's go to L3. In L3's case, alright, we have the x-intercept and y-intercept. We could use intercept form. For the sake of variety, another perfectly good form you might consider here is the very familiar slope-intercept form. So just even though L1 and L3 are very similar, we can just show you two different strategies here. So let's now think in terms of slope-intercept form. Okay, what's that? That's y equals mx plus b. Now, what about m? M is rise over run. Let's imagine going from here to here. The rise is actually negative 1, 2, 3. The run is 1, 2, 3, 4, 5. Okay, so rise negative 3 over run 5. The b is the y-intercept, which is clearly 3. We're often running with y equals to minus 3/5 x plus 3. Now, what about the inequality? We are imagining a half plane up like this. The boundary line is solid. We need to keep that, but then we need to be above this line, having us choose a greater than or equal to situation. Thus we have y greater than or equal to minus 3/5 x plus 3. Okay, L4. Vertical line. Vertical form applies. What's vertical form? That's x equals to a constant. Okay, in this case, that constant happens to be 0. Now, as far as an inequality goes, we want the half plane that is to the right of this line, and it's a solid line, so we want to have the equality case be included. This leaves us with x greater than or equal to 0. Okay, let's summarize our answer here. The system, okay, L1, x over 6 plus y over 8 less than or equal to 1. L2, y greater than or equal to 0. L3, y greater than or equal to negative 3/5 x plus 3, L4 x greater than or equal to 0. Okay, now let's check our work. Okay, now we could do that by selecting some point that's clearly in our system here. For instance, let's say 3, 3. How about that? 3, 3. Surely in the region here, so it's surely a solution. 3, 3 is a solution because it's in the graphed region. Okay, so now let's substitute it into each inequality. Since it's a solution, it has to make each inequality true upon substitution. Here we go. Let's take the first one. 3/6 plus 3/8. How about that? Less than or equal to 1. Well, let's see. 3/6. That's really 1/2. Okay, so that's 4/8. 4/8 and 3/8 is 7/8 altogether. 7/8 is less than 1. True. Okay, next inequality. Y is 3. How about 3 greater than or equal to 0? True. Next, y is 3. How about 3 greater than or equal to negative 3/5 times 3 plus 3. Alright, well, you can, without doing too much arithmetic, say, look, here's a 3 here, here's a 3 there, so far they're equal. All of a sudden there's a negative going on here. This side must be less than this side. It's true. Okay, last inequality, x greater than or equal to 0. X is 3, greater than or equal to 0? Yeah, true it is. Okay, made each inequality true upon substitution. That's what it was supposed to do. So this gives us a little bit of confidence that our system here looks to be correct. Exercise 13. Write a system of inequalities whose solution set is the shaded region. Okay, this shaded region, what about it? It is convex. It has linear boundaries, right? Okay, so observe the region is convex and has linear boundaries. This means the implication is that a system of linear inequalities will work. Need a system of linear inequalities. Okay, well, let's break this up, I suppose. We could call this first line here L1. This one could be L sub 2. This could be L sub 3. Alright, let's take on L1 first. Let's see here. Having 2 points known on the line, we might consider using point slope form. Alright, what's that? Y minus y1 equals m times x minus x sub 1. Okay, now we will need the slope here. So m could equal, in this case here, we could use the y sub 2 minus y sub 1 over x sub 2 minus x sub 1 idea. Call this the sub 2, call this the sub 1 point, and then we'd have 7 minus 5 over 7 minus negative 4, 7 plus 4 in other words. This gives us 2 over 11, And if we look at that line, yeah, 2/11ths, a slightly positive slope, makes sense. Alright, let's put together the equation. Either point can serve as the x1, y1 for right now. Maybe we choose this point here. So this would be y minus 5 equaling 2/11ths, x minusing a negative 4, that's plus 4. Okay, and maybe we want to expand this out. So then this is 2/11ths x plus 8/11ths. Then we can add 5 to both sides. Y equal to 2/11ths x. Okay, 5 would be 55/11ths. 55 and 8. 63. Okay, now that's the boundary line. And checking it out here, is this making any sense with the graph? Is there some consistency here? Okay, the 2/11th slope, that looks fine because it's slightly positive as we ride from left to right on the line. The 63/11ths, okay, let's think about this number here. 55 would be 5, so this is about 5.5, right? Let's go over to this graph, and here's 5, there's 6. Okay, it's having a y-intercept between 5 and 6. That's looking pretty good there. Alright, so the boundary line does look pretty good. Now, we need the inequality that has this boundary line, but the half plane below the line. Since it has this form, below can be done by simply having y less than this. It's a dashed line. We also do not want to include the inequality sign. We finally have y less than or equal to 2/11ths x plus 63/11. Okay, let's go on to L2. In this case, this kind of the information, also just 2 points. So we're thinking, again, point-slope form. That's the y minus y1 equals m times x minus x sub 1. Okay, let's get the slope for this. M would equal, you can use y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And I always use the right hand point as the sub 2 point, the left hand as the sub 1, just because I like to have the x2 minus x1 always be positive. Doesn't matter which way you do it though. Okay, so in this case, 7 minus 2 over 7 minus 3. 5/4. Okay, let's look for a graphic consistency. Remember the perfectly diagonal line, 45 degrees, that has a slope of 1. 5/4. This is a bit more than 1. That looks about right because this line is rather steep, perhaps a bit more than the 45-degree angle line. So we keep going. Let's see, we're ready to choose a point for our line. 3, 2 might be a little easier to work with. This gives us y minus 2 equaling 5/4 x minus 3. Maybe we choose to expand this out here. This further equals 5/4 x minus 15/4. Let's add 2 to both sides. Y would equal 5/4 x. Okay, 2, that would be 8/4. 8/4 and minus 15/4, negative 7/4. Okay, let's check for some graphic consistency there. Negative 7/4. Let's imagine we expanded this L sub 2 line out here. It crosses the y-intercept down here. Looks like it's more negative than negative 1, but not much more. And at negative 7/4, we're at negative 1.75. Okay, we seem to have consistency here. We wanted to keep going. Now that is the boundary line. What about the inequality? Okay, in this case, we need to be above L2. With this form, it's easy to then say we need to then have y greater than, and dashed line, no equal sign, simply greater than 5/4 x minus 7/4. Okay, let's go on to L3. The information here, just these 2 points, again, point-slope form might be a good starting point. So we're looking at y minus y1 equals m times x minus x sub 1. We'll need the slope. Again, we can go with y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That would be, in this case, okay, here, 2 minus 5 over 3 minus negative 4. That's plus 4. This gives us negative 3 over 7. Okay, so now we're looking at y minus, we'll choose this to be the point, I suppose. Y minus 2 equaling minus 3/7 x minus 3. And by the way, this negative 3/7 slope, graphic consistency, because this line is somewhat downhill as we ride along left to right, having us think negative slope. And it's not as negative as the negative 45-degree line, so it should not be like negative 1. It should be a fractional negative, and it is. Okay, anyways, we continue here. Maybe we choose to expand this out. So this equals minus 3/7 x plus 9/7. We could now add 2 to both sides if we wanted to. Y could equal negative 3/7 x. 2 is 14/7. 14 and 9 is 23. Plus 23 over 7. Let's see if we like this. 23/7, that's somewhat more than 3. 3 and 2/7. Let's look at the y-intercept of this L3. 1, 2, 3, and a little bit more. Okay, 3 and 2/7 looks very consistent. So this seems to be going well. The inequality, we need to be have a half plane above L3. We choose a greater than sign. This is solid. We choose a greater than or equal to sign. We've got y greater than or equal to minus 3/7 x plus 23 over 7. Okay, let's get our answer formulated here now. The system we have in mind could be as follows. The one we got from L1, this is y less than or equal to 2/11 x plus 63/11. Okay, L2, y greater than 5/4 x minus 7/4. And the L3, y greater than or equal to negative 3/7 x plus 23/7. Okay. Now, let's try to give this some kind of check over. Let's take a point that's surely in the region here. Okay, sometimes I look at these fractions and pick something that'll make them all come out nicely, but we have 7ths, we have 11ths, and 4ths to work with. It's going to be hard to pick a number that makes them all nice and pretty when we substitute. So just pick something that's maybe surely in the region, not too complicated. How about we go to 4, alright, maybe 3, 5. Okay, no doubt about it, it's in the region. It should make each of these true. Okay, so here goes our check. We're saying that 3, 5 is in the region. So it's a solution. Substituting into each inequality, here's what we would get. Let's take the first one. 5 less than or equal to 2/11 times 3 plus 63/11. Okay, 2 by 3 is 6. That's 6/11. 6/11 and 63/11. That's 69/11. 69/11 would be 6 and 3/11. That's greater than 5. This is true. Okay, second inequality. 3, 5. 5 for y. 5 greater than 5/4 times the x is 3 minus 7/4. Let's see. Here's 5 by 3 is 15. 15/4 here. 15/4 minus 7/4. Okay, that's 8/4. It's 2. 5 is greater than 2. This is true. Okay, the third inequality. The y is 5 greater than or equal to negative 3/7 times 3 plus 23/7. Okay, let's see here. 3 by 3 is 9. Here's 9/7. Negative 9/7 plus 23/7. Okay, that knocks us down to 14/7 or 2 on the right-hand side. 5 is greater than or equal to 2. That's true also. Okay, so it seems like this is looking pretty good. All right. Exercise 15, Part A. How does the indicated region differ from the indicated regions of exercises 9 through 14? All right. So we have this indicated region here. And, just for a quick review, let's take a look at 9 through 14 one more time, real briefly. All right. Here was the region from exercise 9. There's the region from exercise 10. 11, 12, 13, 14. What about all these? What's their one common feature? Well, you'd have to say they're all convex, right? Any 2 points in the region, if you connect them with a line segment, that line segment also is in the region. True for each of these, right? Okay. Or sometimes it's more, a cruder version of convex is to say that the region bulges outwards all the times. Okay, like that too. All right. Well, let's take a look at again at this region here in number 15. And you know what? It's got an indentation, and this is going to be concave. In other words, more specifically, if you select, say, this point and this point, and now you connect those two with a line segment, that line segment would not lie entirely in the region. Okay, so that means this is a concave region. All right, so we can record this. The indicated region is concave. Each of the regions in numbers 9 through 14 was convex. Okay. Part B. Is it possible to write a single system of linear inequalities whose solution set is the indicated region? You know what? No. The solution set of a system of linear inequalities is always convex. or empty, but for most purposes, considering that it's always convex. Alright, and just to maybe elaborate a little bit here, if you were to do something at all with inequalities for this region, you might consider breaking it up into a couple of regions which are divide it there, maybe call this R1 and this R2, and so now you have the region, the indicated region is equal to R1 union with R2. Then you could come in here and you could describe this as a solution set to a system of inequalities linear inequalities, and then you could describe this as a second solution set to a system of linear inequalities. And when you've written those two systems, you then have to put the word or between them so that you get the union of their two solution sets to create this indicated region here. Okay.